potentiometric titration, two type of titration, to determine the end point of titration. Determine the end point of titration. First one is classical method for locating the end point. Then how to determine the end point of titration? First one is classical method and second one is analytical method. In classical method, for example, whenever the volume of solution is added, in burette and x-axis and y-axis is measure the EMF. You already known that in potentiometric titration measure the EMF or cell potential or reduction potential. Whenever the volume of solution is added during the titration, the EMF is slowly increase. And after some time EMF is sharply increase. EMF is sharply increase. After the sharp increase, again EMF is slowly increase. This sharp point of this graph is called as equivalence point or end point of titration. In this classical method, to determine the end point for this time. In classical method, end point determined like this. This is the classical method for the locating the end point of titration. This type of curve is called as sigmoid curve. Means determination of titration or determination of end point of titration like this method for classical method. And second one is analytical method. Analytical method. Second one is to use the analytical method to determine the end point of titration. In both this method, analytical method is correct method to determine the exact end point. For graphical representation, x-axis is same as volume of solution and y-axis to determine the delta E upon delta V. This is the first derivative method for determination of end point of titration. Analytical method, there are two methods. First derivative method for determination of end point of titration. In x-axis is the same volume of solution and y-axis is the delta E upon delta V. After the titration, whenever the delta E upon delta V is increase and after some time again decrease, this is the end point of titration. This is the exact or correct method or exact end point to determine the analytical method. This is the first derivative method. To determine the end point of potentiometric titration by using analytical method. This is the first derivative method. And next one is second derivative method. This is the same like, but in this graphical representation, x-axis is the same volume of solution and y-axis is called as delta E square upon delta V square. The nature of the graph like this. This is the end point of titration. This is the first derivative method and this is the second derivative method. In this both classical and analytical method, why are use the analytical method? Because analytical method used to correct or exact end point of titration. Exact end point of titration, this is the exact, and in the second this is the exact end point of titration. Then next is, there are three type of titration in your syllabus. First is acid base titration. Acid base titration. Second one is redox titration. Second one is redox titration. Third one is precipitation titration. Third one is precipitation titration. Now first see the redox titration. First see the acid base titration. First see the acid base titration. Acid base titration. Acid base titration. This titration is also called as neutralization titration. Also called as neutralization titration. Also called as neutralization titration. First is acid base titration. This acid base titration is also called as neutralization titration. In this titration, acid is neutralized by neutralized by neutralized by base. Acid is neutralized by base. Acid is neutralized by base. Acid means H plus ion concentration present. H plus ion concentration present. In this titration, in experimentally take a beaker. In this beaker, use the HCl solution. Use the HCl solution means in this solution present H plus ions. In this solution present H plus ions, and dip the any one indicator electrode. This is the indicator electrode. Dip the any one indicator electrode. For example, hydrogen electrode. This is the dip the indicator electrode. For example, hydrogen electrode. Hydrogen electrode. Cunhydron electrode. This is already known that indicator electrode, and this is coupled with this is coupled with saturated calomel electrode. This is coupled with saturated calomel electrode. This is coupled with saturated calomel electrode. This is the reference electrode. This is the reference electrode. This, take the beaker and take the HCl solution. In the HCl solution means H plus ions are present. This solution dipped to any one indicator electrode, for example hydrogen electrode, cunhydron electrode, and this electrode is coupled with another electrode is called as saturated calomel electrode. This electrode is called as reference electrode. In this HCl is added cunhydron powder. Cunhydron powder. Cunhydron powder. Pinch of, in this HCl solution added pinch of cunhydron powder. Take the HCl solution and added the cunhydron powder, and this solution dipped with any indicator electrode, and this electrode coupled with another electrode is called as saturated calomel electrode or reference electrode. Then this is the burette. This is the burette. In this burette, take the NaOH solution. Take the NaOH solution. Take the NaOH solution. It is called as acid-base titration. Take the HCl solution and in burette NaOH solution. Then this is the graphical represent. How to representation of say? First, saturated calomel electrode. Double line means this is the salt bridge is important. This both electrode are coupled with salt bridge. This both electrode are coupled with salt bridge. Saturated calomel electrode is negative. This is the negative. This is the positive. Saturated calomel electrode double slash means salt bridge. In this solution, H plus ions, H plus ions, then H2Q plus Q. This is the Cune hydrone powder. Cune hydrone powder. Cune hydrone powder and platinum electron and platinum electron. This is the representation of the cell. Saturated calomel electrode, H plus ions. This is the platinum electrode. This cell is coupled with another cell by using salt bridge. Whenever the titration is carried out, when the addition of any wedge, HCl means this is the acid. This is the acid means pH is below the 7. Below the 7. Below the 7. Acid means pH 0 to 7 acid and 7 to 14 base. This is the pH range. Whenever the HCl is acid means pH is below the 7. Whenever the addition of any wedge, in this HCl, H plus ions, H plus ions are decrease. H plus ions are decrease means acidity decrease. Acidity decrease means decrease means pH is increase. pH is increase. In graphical representation, this is the volume of any of which, and here EMF. Volume of any wedge, and this is the EMF. EMF is depends on concentration of ions present in the solution. Depends on concentration of ions present in the solution. EMF is depends on concentration of ions present in the solution. During the titration, whenever the addition of any wedge in any wedge, H plus ions are decrease. Whenever the H plus ions are decrease, already acidity is decrease. Acidity decrease means pH as well as increase. In graphical representation, volume of NaOH on x-axis and EMF on decrease. EMF is depends on concentration of ions present in the solution. H plus ions are decrease means EMF is decrease. EMF is depends on concentration of ions present in the solution. Means first, without addition of NaOH, in this solution present H plus Cl minus ions. H plus and Cl minus ions are more. That's why EMF is more. Initially EMF is more. Whenever the addition of NaOH, H plus ions are decrease. H plus ions are decrease. Already H plus ions are decrease means EMF also decrease. Whenever the titration is carried out, then addition of NaOH is H plus ions are decrease, EMF is decrease. Again NaOH is added, EMF is decrease. Then near the equivalence point, sharply decrease the EMF. Near the equivalence point, this is the equivalence point. Sharply decrease the EMF. Then after the equivalence point, again slowly decrease the EMF. This is the equivalence point of titration. Or end point of titration. Whenever the H plus ions are decrease, EMF is decrease. That's why initially without addition of any wedge, EMF is more. EMF is more. When addition of any OH, H plus ions are decreased. For example, see H plus plus Cl minus. When the addition of NaOH, then H plus plus Cl minus plus Na plus OH minus. Na plus OH minus. This H and this OH gives the H2O and this form the NaCl. This form the NaCl means this H plus ions and OH minus ions are react to form the H2. That's why this H plus ions are decrease. The EMF is decrease. EMF is decrease. That's why this curve is decrease the EMF. Decrease the EMF. Decrease the EMF. This is the classical method. This is the classical method to determine the end point of titration. To determine the end point of titration. Then analytical method to determine the end point of titration. In analytical method, see the volume of NaOH. You already know that delta E upon delta V, and this is the analytical method to determine the end point of titration. End point of titration. This is the analytical method to end point of titration. This is the first derivative method, and next one is this is the here volume of NaOH and there delta E square upon delta V square. This is the end point of acid base titration. End point of acid base titration. This is the first titration to determine the end point of titration. This is the acid base titration or neutralization titration. Why called as neutralization titration? Because in any titration to form the H2O molecules here, in any titration to form the H2O molecule, that titration is called as neutralization titration. That titration is called as neutralization titration. Any titration to form the H2O molecule, that titration is called as neutralization titration or acid base titration. This is the acid base titration.